In this video, we will be solving this question which says, show that the following system of equations lambda x plus y plus z is equal to 1, x plus lambda y plus z is equal to lambda, x plus y plus lambda z is equal to lambda square has a unique solution provided lambda is not equal to minus 2 and lambda is not equal to 1. Find the solution. Explain the nature of the solution when lambda is equal to 1. Now we can write the above system of equations in the matrix form, that is your lambda 1 1 1 lambda 1 1 1 lambda. These are all the coefficients of x, y and z. In the first column we are writing the coefficients of x, in the second column we are writing the coefficients of y, and in third column we are writing the coefficients of z. And here are your x, y and z, and this is equal to 1 lambda lambda square. This entire matrix is your A. This entire matrix is your x and this entire matrix is your b. Let's first find the determinant of A, that is lambda 1 1 1 lambda 1 1 1 lambda. Opening along the first row, I get lambda is equal to lambda square minus 1 multiplied by lambda minus 1 plus 1 multiplied by 1 minus lambda. Simplifying this, you will get that determinant of A is equal to lambda cube minus 3 lambda plus 2. And again, finding the roots of it, you will get that this is equal to lambda minus 1 whole square multiplied by lambda plus 2. Now we know that Ax is equal to B. Re-multiplying both the sides by A inverse, I get A inverse multiplied by A multiplied by x is equal to A inverse B. And by the properties of matrices, I know that A inverse multiplied by A is equal to the identity matrix, that is your I. So your Ix is equal to A inverse B, and identity matrix multiplied by any matrix is equal to the matrix itself. Thus your X is equal to A inverse B. Now from above we can imply that for solution of system of equations, A inverse should exist, which happens A is invertible, which further implies that determinant of A should not be equal to 0. Thus, for unique solution, I want that the determinant of A should not be equal to 0. And the determinant of A was lambda minus 1 whole square multiplied by lambda plus 2. And this should not be equal to 0. This means that your lambda minus 1 whole square should not be equal to 0 or lambda plus 2 should not be equal to 0. This means that lambda minus 1 whole square should not be equal to 0 and lambda plus 2 should not be equal to 0. Note that I am writing and here, because had it been the case that lambda minus 1 whole square plus lambda plus 2 is equal to 0, if there would have been equal to, then either term being equal to 0 would suffice. But we want that this should not be equal to 0. Thus, it has to be the case that this should not be equal to 0 and this should not be equal to 0. If this is equal to 0, then anything multiplied by 0 is equal to 0, which will not satisfy this equation. So do keep these things in mind, that when you're dealing with not equal to, we get and, that is both the conditions should satisfy. And when this is equal to 0, then we write that lambda minus 1 whole square is equal to 0 or lambda plus 2 is equal to 0. Here we are fine when either this is true or this is true. It could be the case that this is not true but this is true, but that is okay with us. But in this case, both the conditions should be true. So now solving this, I get that lambda should not be equal to 1, and solving this, I get that lambda should not be equal to minus 2. Thus, your determinant of A is not equal to 0 when, incorrect, sorry on my part. So when lambda is not equal to 1 and lambda is not equal to minus 2. Thus, for the unique solution, we want that lambda should not be equal to 1 and lambda should not be equal to minus 2. Now, let's find the solution. We have x is equal to A inverse B. We have x, we have B, but we do not have A inverse. So let's find that. As you must be knowing that A inverse is nothing but the adjoint of A divided by the determinant. Now, we have A as lambda 1 1 1 lambda 1 1 1 lambda. Now, how do you find the adjoint of A? Firstly, you have the signs, that is, it goes like positive, negative, positive, negative, positive, negative, positive, negative and positive. Now, if you want to find this element, all you have to do is eliminate this column and eliminate this row and multiply this with this minus multiplying this by this. That will give me lambda square minus 1, and we have already written the signs. Now let's try and find this element. This element belongs to this line and this line. So we will eliminate this line and this line, and we will multiply, that is 1 multiplied by lambda, that is lambda minus 1, that is lambda minus 1, and we have already minus in front of it. Again, let's try and find this element. This element belongs to this line, so we will be eliminating this line, and this element belongs to this line, so we will be eliminating this line. That would give me 1 multiplied by 1, that is 1, minus 1 multiplied by lambda, that is 1 minus lambda. Similarly, you can find all the remaining elements. If you notice, you can see that this can be written as lambda minus 1 multiplied by lambda plus 1. And we have lambda minus 1. But here we have 1 minus lambda. So taking minus 1 common, I will get that minus of lambda minus 1. Similarly doing so here. Now, why I am doing so? Because now I can take lambda minus 1 common from the entire matrix. Note that this is not the determinant. We are dealing with the matrix here. Had it been the determinant, then we were taking out lambda minus 1 from this row, and from this row. Then we would get the value of lambda minus 1 whole cube. But we are dealing with the matrices here, and this is just a number. That's why we have the power of 1 here and not 3. So thus the adjoint of A becomes lambda minus 1 multiplied by this matrix. And now your A inverse is equal to adjoint of A divided by determinant of A. This is your adjoint and this is your determinant. So now this gets cancelled with this. So you are left this matrix. So your A inverse is this matrix multiplied by 1 divided by lambda minus 1 multiplied by lambda plus 2. Also, our main objective was to find X and not A inverse. Your X is equal to A inverse B. Now post multiplying A inverse by B, I will get this. Doing all the calculations, I will get that your X is equal to 1 divided by lambda minus 1 multiplied by lambda plus 2 is equal to minus of lambda minus 1 multiplied by lambda plus 1. This is your lambda minus 1 and this is your lambda minus 1 multiplied by lambda square plus 2 lambda plus 1. Now again I can take lambda minus 1 common, and now I am left with only this thing, that is your lambda minus 1 and lambda minus 1 gets cancelled. My X is minus lambda plus 1 divided by lambda plus 2. Y is equal to 1 divided by lambda plus 2 and Z is equal to lambda plus 1 whole square divided by lambda plus 2. Now the question asks, what is the nature of the solution when lambda is equal to 1? When lambda is equal to 1, my system of equations become this, which means in the matrix form this can be written as this. And your determinant is equal to 0. This means that there does not exist a unique solution. But there can exist a solution. I am not saying that there won't exist any solution. I am just saying that there won't exist a unique solution. Now let's find if the solution exists or not. And to do that, we have to find the rank of A augmented B and the rank of A. Now the rank of A augmented B is 1 and rank of A is also 1. And the number of unknowns is 3. That is X, Y and Z. Now your number of unknowns is greater than the rank. Therefore, you have infinitely many solutions. Thus when lambda is equal to 1, you will have infinitely many solutions.